più gente l'altro talk.
Hello, everybody. Welcome to the seminar. Today it is my pleasure to introduce you to Matteo Miluzio, who obtained his PhD in the astronomy department of Padua, Italy, under the supervision of Enrico Capellaro. The topic of his PhD project was about supernova search, and he was entitled HAWK-1 Infrared Supernova Search in Starburst Galaxies. After his PhD, during the 2 years, he obtained 2 scholarships for about 8 months, and he worked. He studied the photometric and spectroscopic properties of a sample of tape 1A supernova. He then moved here, and this is his first official postdoc. So thank you, Matteo.
Exactly. Thank you very much. Good morning to everybody. Yes, I'm Matteo Miluzio, and today I present the results of my PhD works, and then I will show the plans for the next month here at IASM. Of course, during my PhD project and only after the PhD, I followed other kinds of projects in different topics, but today I speak only about my PhD work because it is more interesting and more related to the thing that I will have to do here in the next month. This is the outline of my talk. The main part is focused about my PhD project, an infrared supernova search in starburst galaxies, and the final part of the talk, I explain my plans for the future months. Okay, this is the title of my PhD work, an infrared supernova search in starburst galaxies. The first question is why supernova rate? The rate of supernova is a crucial quantity in astrophysics. Supernova dominated the chemical evolution of the universe and the dynamical properties of the interstellar matter, providing at least part of the feedback needed to explain the galaxy evolution. Corcola supernova rates trace directly the current star formation rate due to their short-lived progenitors, while the rate of type 1a supernova trace the whole history of the star formation because of the long delays of their progenitor. The type 1a supernova are believed to result from the thermonuclear explosion of the type of a white dwarf in a binary system. Recent studies on the Corcola supernova progenitor set a lower limit of 8 solar masses for the Corcola progenitor mass range. And if this value is accepted, it was claimed that the Corcola supernova rate is a factor of 2 smaller than those predicted by the observed cosmic star formation rate, sometimes called the supernova rate problem. While we should keep in mind the uncertainties on star formation rate calibration, several explanations have been proposed, but the main bias seems to be the underestimation of the Corcola supernova population due to the presence of high extinction, particularly in the nuclear region of the galaxies. In fact, several authors, and more recently Mattila 2012, argued that a large fraction of Corcola supernova are missed in optical surveys due to dust obscuration, in particular in the nuclear region, with a loss of up to 90% in luminous and ultraluminous infrared galaxies. So, entering this debate, we planned for a new infrared supernova search in starburst galaxies, with the aim to verify the link between star formation rate and supernova rate in an environment where the star formation is very high, 1 or 2 orders of magnitude higher than the the normal compared to the normal star-forming galaxies. Of course, this high star formation rate imply a nice supernova rate of about up to 1 supernova per month. But starburst galaxies are interesting for another feature because they have high content in gas and dust. Since the ultraviolet radiation coming from young and massive stars is absorbed and then re-emitted in the far infrared, the bolometric luminosity of these galaxies is dominated by the far infrared luminosity that then become an ideal tracer of the star formation. But despite the fact that an high star formation rate implies a high supernova rate, no supernova was found in starburst galaxies up to 2000. The first attempt to measure supernova rate in starburst galaxies in the optical band backdated to 1998, thanks to Richmond, with only a handful of events discovered, but no supernova, no confirmed supernova. They explain this fact with the presence of a bias due to high extinction at optical wavelengths. So the missing supernovae are expected to show up at longer wavelengths where the extinction is strongly reduced. In particular, for example, in the infrared, in the K-band, the extinction is about 10 times lower than the extinction in the visual band. Some attempts of infrared search, supernova search in starburst galaxies were made both with ground-based telescope and with space telescopes. Sorry, but they discovered only few obscured supernova. Particular, for example, Crash et al. 2007, using the near-infrared camera of the Hubble Space Telescope, found only one possible event. This is a supernova without the spectroscopic confirmation in the galaxy ARP 2020. So, the main conclusions of this work are two. The first one is that they confirm that the near-infrared searches are more efficient than optical searches. But at the same time, the majority of the supernova expected from the far infrared luminosity are still missing. In fact, the supernova detection rate is about 3 to 10 times lower than expected from the far infrared luminosity. And the possible explanation is the presence of very high extinction, greater than 30 magnitude in the nucleus of starburst galaxies. But at that period, the statistic was very poor. So many of the original questions remain unanswered, and this gave us the motivation to make a new attempt exploiting the opportunity offered by OCAI, that is the cryogenic near-infrared imager mounted at the Naismith A focus of the UT4 telescope at the ESO Paranal Observatory. The wide field of view, that is about 7.5 arc minutes per 7.5 arc minutes, and the pixel scale of only 1.1 arc second per pixel, allowed us to observe whole galaxies and pairs of galaxies with an excellent resolution. This is important, in particular for the nuclear regions of the galaxies. For this search, we selected a sample of 30 local starburst galaxies from IRAS catalogs with redshift less than 0.07. With this distribution in far infrared luminosity, you can see that the majority of the galaxies are luminous infrared galaxies, while two of the galaxies of the sample are ultraluminous infrared galaxies. Another constraint is the visibility at ISO from April to October. In this plot, in this figure, I show the blue and the total infrared luminosity distribution of the galaxy of the sample, as is expected from starburst. The total infrared luminosity is about 10 times greater than the blue luminosity. This confirming the fact that all the galaxies of our sample are actively star forming. some words about the search strategy. Given that the infrared supernova light curves evolves relatively slowly, an infrared search did not require frequent monitoring, so we planned for about 3 visits per galaxies per semester. That implied total request of about 100 visits. Another important characteristic is that our program was a filler with no restriction on seeing and sky transparency condition. As I said before, for the imaging we use OCI at WLT, and for the spectroscopic confirmation of the candidates we use ISAC at WLT in TO mode during the first period, and the X-shooter at WLT using GTO time in the next 2 periods. Okay. Data reduction was performed integrating the ESO receipt execution tools with custom programs in a Python environment. The pipeline is divided in 4 main steps. The first one included the pre-reduction, the astrometric calibration, the creation of the stacked images from the mosaic detector of the OCI field of view. You can see here the 3 examples, the final images. You can notice the excellent quality of the images. I choose these 3 galaxies because are representative of the heterogeneity of the sample, because we have single galaxies, we have pairs or close pairs of galaxies, and finally strongly interacting galaxies. This is important because as I will show later, the galaxy morphology is strongly related to the concentration, to the distribution of the star forming activity inside each galaxy. The second step of the pipeline is the image subtraction between images taken at different epochs with eases for the PSF matching. You can see an example of the image subtraction. In this case, we found the supernova 2010 HP. This is the discovery image of 2010 HP. You can see here an excellent result of the image subtraction, but in many cases the images showed significant presence of spurious residuals due to the luminous nucleus, in particular when the seeing of the images was very poor. The search of transit candidates in the different images led to the discovery of 6 supernovae, 5 core collapse and 1 type 1a supernova. In these 2 cases, we obtained the discovery image of the supernova, the 2010 HP and 2011 EE. In these other 2 cases, unfortunately, the supernova was discovered before by other groups, so we rediscovered these 2 objects independently. This is the supernova 2010 GP is the only one type 1a supernova in our sample. And these 2 other cases, the supernova was too faint to obtain spectroscopic classification. The signal to noise of the spectra was too low. But we are sure that these are 2 supernovae because we have this detection in more than one epoch. So this is not simply a residual of the image subtraction. The last step of the pipeline, but I think that it is the most important step, is the estimate of the detection efficiency through artificial star experiments. In fact, in order to derive the supernova rate from the number of observed events, it is crucial to obtain an accurate estimate of the detection efficiency of the search. So through artificial star experiments, we estimated the magnitude detection limit for each of the images. And different location in the images. To illustrate the results, I show here the plot of the magnitude limit versus counts for a given galaxy. Remember that this is the galaxy NGC 17130. Of course, the nuclear region is in the direction of the higher counts, and I plot here. These lines are 4 different epochs for this galaxy with the different things. You can notice that in the outskirts of the galaxy, the magnitude limit is about roughly the same for all the 4 epochs. While in the nuclear region, the magnitude limit is, as expected, much lower, even 4 or 5 magnitudes lower than in the outskirts. This is due to the fact that, in particular for the images with basing, the presence of residuals is become very important, and this implies that, of course, the magnitude limit is brighter in this region, in the nuclear regions. So, to evaluate the significance of the observed events, we developed a Monte Carlo a simulation tool that computes the number and the properties distribution of the expected events. Based on a specific assumption and feature of our search. In particular, you can see in these 4 boxes the basic assumption of the simulation tool about the characteristic of the search, our knowledge about supernova and stellar physics, and about the properties of the galaxy of the sample. And in particular, these 3 points are very important because are the major source of uncertainty in the simulation, but I will discuss later in more detail. The tool uses a Monte Carlo approach that simulates the stochastic nature of the supernova explosions, and by collecting several Monte Carlo experiments, we test whether the observed events are within the expectations, and finally, to test the influence of a specific assumption, we varied some of the input parameters in the Monte Carlo simulation. So these are the parameters for the reference simulation. We use the Kenny-Cut calibration for the total infraluminosity and star formation rate. We use the Salpeter AMF. We assume that the core collapse mass range progenitor is in the range of 8 and 50 solar masses. We, as a first order approximation, we assume that the extinction follow the star formation rate distribution with the maximum value of about 30 magnitude in the nuclear region. But the most important point is the distribution of the star formation. Why? This is because we expect that the supernova are more frequently in the region of with high star formation, where on the other hand the detection efficiency is much lower. In principle, we know that mid-infrared and far-infrared luminosity are a good tracer of the star formation, the distribution of the star formation. But the problem is that our images are all in K-band, and is well known that the K-band, that the near-infrared emission traces all the stellar population, which is the galaxy mass distribution, better than the star formation rate distribution. So, for this reason, we are forced to have an idea of the compactness of the starburst activity. We are forced to an indirect statistical approach. So, firstly, we have to know the size of the starburst inside each galaxy of the sample, and to do this we follow the work of Hattori 2004, who derived a correlation between the global starburst properties, such as the far-infrared colors, the size of the starburst activity in the galaxies, and the galaxy morphology. And I found that disturbed galaxies tend to have more compact starbursts. Following this approach, we found that about 45% of the galaxies of our sample are characterized by nuclear starbursts, while about 55% of the galaxies are characterized by extended starbursts. And if we classify morphologically aerogalaxies, we obtained a confirmation of the work of Hattori. In fact, we found that disturbed galaxies seems to have more concentrated starbursts. Now, we know the size of the starburst activity. The problem is that how the star formation rate could be related to the K luminosity. And to do this, we follow the work of Solfer 2001. For several galaxies, they plotted the near-infrared, the mid-infrared, and the near-infrared emission curve of growth, finding that isolated galaxies tend to have the near-infrared emission and near-infrared emission with the same trend, while interacting galaxies seems to have a near-infrared emission that is more concentrated. We re-elaborated their plot, and we found that to a first-order approximation, the mid-infrared emission seems to be well matched by near-infrared emission powered to an exponent alpha, and this is important. With this exponent alpha ranges from 1.2 for galaxies with a standard starburst to 1.5 2 for galaxies with very compact starburst activity. And this is one of the most important assumptions in our simulation. As said before, the outcome of the simulation are the number and properties distribution of the expected events. Here I show the histogram of the number of the expected events in our simulation with the Poissonian uncertainties, that is the gray area, compared to the observed events, that is the dashed vertical lines. And you can see that there is an excellent agreement between these two numbers, 5.4 against 6. This is very important because observations are within the expectations. Only as a test, we sorry for the color, but we compute the expected rate using the blue luminosity instead of the far infrared luminosity, and as expected, we found an expected rate that is much lower than the reference case. And this is only another confirmation of the fact that our galaxies are all actively star forming. Finally, to understand how the different choice of the test parameters can influence the final expected rate, we varied each of them and computed the rate repeating the Monte Carlo simulations. These are the main source of uncertainties. In particular, if we change the lower mass limit of the core collapse progenitor mass range from 8 to 10 solar masses, we found that the expected rate is much lower, about 30% lower. Another important point is that the uncertainty on the extinction does not significantly affect the final rate. This is an important result because we obtained that the variation on the expected rate is significantly only if extinction is much high, about greater than 200 magnitude, but this is value is unlikely because it's not present in the literature. So this is the third main source of uncertainties. It is the main source of uncertainties as expected about the star formation assumption about the star formation distribution. If we assume that all the galaxies of the sample are characterized by a standard starburst, so alpha equal to 1, we expect to found more supernova. In fact, the supernova rate in this case is about 40% higher than the reference case. Conversely, if we assume that all the galaxies of the sample are characterized by compact starburst, that implies that alpha is equal to 2, the number of supernova expected is much lower, of course, about 35% lower, because all the supernovae are in the nuclear region where our detection efficiency is much lower. We analyzed also an ideal case with the detection where the detection efficiency is the same in the nuclear, where the detection efficiency in the nuclear region is as deep as in the outskirts of the galaxies, and where the extinction is negligible, and of course we obtained an expected rate that is much higher than the reference case, about 60% higher. What this means? This implies that 60% of the supernovae are missed in the nuclear regions due to the combined effect of high extinction and the lower magnitude limit. But we know that from this point that the main source of uncertainties is just the magnitude limit. So to conclude this first part of the talk, these are the main conclusion. We found that the observed rate of the supernova in starburst galaxies is consistent with expectation. We confirm also the fact that starburst galaxies are more active than normal galaxies as expected. At the same time, we confirm that about 60% of the supernovae are still missing. Previous work says that this is due to a very high extinction, but our explanation is that the missing supernovae are in the nuclear regions where the lower magnitude limit is the dominant bias and not the extinction. In fact, the extinction could be very high in the nucleus, but these have a small influence on the expected rate. Another important conclusion is that the star formation in starburst galaxies is concentrated, but there is also an extended component. The size of the starburst depend on the galaxy morphology. We found that disturbed galaxies have more compact starburst. Well, now I show briefly the plans for the next months here at ESA within the Starburst and EMIR projects. The task will be mainly to participate in the test in the lab and to test and customize the exposure time calculator of EMIR. To collaborate in the commissioning of the instrument at La Palma. In the second part of the work, I have to compile the catalog of starburst for EMIR and to carry out the simulations of the observation with EMIR of the targets in the catalog. And these are the people and the Institute that participate to the commissioning of the instrument. Okay. EMIR is a wide-field near-infrared camera spectrograph operating in the near-infrared domain from 0.5 to 2.5 micrometer using cryogenic multi-slit masks. So EMIR will provide a 10-meter class telescope like the Grand Tecan with imaging, long slit, and multi-object spectroscopy capabilities in the near-infrared wavelengths. These are some of the top-level instrument parameter of EMIR. In particular, you can see that the top priority is the multi-object spectroscopy in K-band, and that the expected spectral resolution is about 500 in J, 400 in H, and in the K-band. For the image mode, the field of view is about 6.57 per 6.7 arc minutes, while in the multi-object spectroscopy mode is smaller because it is limited by the grid of the 55 slits. As said before, one of the things that I will have to do is to test and customize the ETC, the exposure time calculator, in particular in the provision to put the interface of the ETC in the EMIR website. But how? One moment. Okay. Which are the requirements that a tool like the exposure time calculator should be cover? The ETC and tool should allow current and future user to prepare efficient observation with EMIR, of course. So the ETC should accommodate the photometry and spectroscopy of both point source or extended objects. Should be cover all the instrument setups and all possible combination of filter and GRISM. Should model, in particular in the infrared observation, this is very important. The ETC should model the sky emission, and should allow some freedom for the choices of the user about observing mode or how the sky is measured. Another important thing is the possibility to choose the width and the length size of the slits, and the possibility to use different spectral templates in input, for example, black body spectrum or Gaussian emission line. Another important point is that it could be very useful if there is the possibility for the user to use a proper set, a proper spectral energy distribution. The output of the exposure time calculator should be the estimate of the signal to noise for as a function of time or wavelength for a given configuration and observing time, and possibly the warnings regarding the saturation in the detector for both object and sky. This is the preliminary version of the user panel of the exposure time calculator with 5 main areas. The first one, in the first one, you must input the observed magnitude in a given band and whether you are observing a point or extender source. And the second one, you can choose the spectral energy distribution in input. You can choose for 4 different model of spectral energy distribution. The first one is the model library, in which you can choose the preload models from the Pickle Stella library. With the model file, the user can provide a proper spectral energy distribution. If you choose black body, a black body set will be used, and you have to specify the temperature of the black body in this text field. This choice is important, in particular for the emission line for very useful for very faint object in which the continuum is not visible. So you can choose the characteristic of a specific emission line. These are simply parameters related to the observed condition, the Hermite and the Sing. And in this box, you have to input. You must input the data about your photometric observation. In this case, the output is the estimate of the signal to noise expected for one exposure time. In this case, the signal to noise is estimated only for that number, or a range of exposure time. In this case, the signal to noise is estimated and plotted versus time for the whole range of the exposure times. This, for example, the output is only, it's not a real case, of course. You can see that this is the plot of the signal to noise per pixel versus the exposure time. Another useful output is this table, because you can check whether you reach saturation for one of the exposure times. And this is the same for the spectroscopy. Is the same. The output is the same. You have to choose only the slit width and exposure time. That is the exposure time, as in the previous case, is only a number or a range of numbers. And this is the output. It's the signal to noise per pixel, the normalized flux versus the wavelength. And the idea is to put this interface, is to include this interface in the EMIR website. It is only a beta version of the EMIR website, in order to make the ATC usable for the user, of course. And this is a summary of the verification status of the EMIR instrument. All mechanisms are fully functional. In particular, for example, about the DTU, one of the mode of the DTU, we had a problem with one of the mode of the DTU before the beginning of the last verification phase, but at the moment it is solved. So we are just in the beginning, in the middle of the last verification phase. Another important point is the dispersion for each filter. You can see here, for example, the average resolution compared to the expected. It's a very good result. And the plan for the commissioning, we have to complete the stage 3, that is divided in 2 main cycles. The first one is with the pinhole mask in the focal plane, is aimed at configuring the DTU, that is the detector translation unit, flex correlation mode, and the fine-tuning of the detector parameters of the different readout modes. And the second part of the stage 3 is mainly to test the behavior of the CSU, that is the cryogenic slit unit, in the EMIR instrument prior to the final acceptance of the instrument. So hopefully we have to ship and execute integration and at the ZTC, and the crucial date is for late summer of 2015. And that's all. Thank you.
Thank you, Matteo, for this interesting talk. Is there any question?
So I have a stupid question, maybe I didn't get it. So these are the supernova explosion events or supernova remnants? So how young are these objects that you are tracing in?
These are supernova explosion.
These are explosions, so
Yes,
they are
yes.
very young. Okay. And then how do you distinguish between these explosions and the other kind of, I don't know, star forming phases of the star formation, like, I don't know, H2 regions and this?
Yes, because
yeah.
The first thing is to recognize a supernova between, for example, other residuals in the images. The first thing is that if we detect the residual in more than one epoch, we are sure that is not a residual due to, for example, bad subtraction. This is the first point. Then, with the difference of observation, we obtain the light curve of the supernova. So, comparing this light curve with the library of standard supernova light curve, we are sure that these objects are really a supernova. We also are able to recognize the type of the supernova with this comparison.
Okay.
It is, for example, a type 2, type 1c, or type 1a supernova. We have also, in 4Ks, the spectra of the object, and this is another confirmation that
Okay, so
our
then
object
probably you can also have some prediction for the far infrared emission for these events, or even longer wavelength. Probably you can have some prediction based on this spectrum as well.
Yeah.
Okay, thank you.
So it seems to me that EMIR is a good instrument to use to continue your PhD
Yes.
project. I mean, have you thought about using, following up the search, maybe going deeper and then doing spectroscopic
Yes,
follow-up
of
of these
course.
objects? Yeah.
it should be an idea.
Obvious. Yeah.
Yes, yes.
Yeah, I have two questions. The first one is that because you have different interacting systems or different phases, let's say, so do you find supernova more efficiently in any particular morphology or places within the interactions, like in the tails or the bridges?
Yes, for example, we found that one moment. No, it's before. Okay. So you okay. Yes, this is a good question. For example, we found that all our events are located very close to, for example, H2 regions, or in the correspondence of spiral arms or tidal tail. Why? In this case, this is type 1a supernova that is very far from all all the star forming region of the galaxy. So it is not a clear relation between the because, for example, this is a single galaxy. This is a single galaxy, or this is also a single galaxy. This is another single galaxy. So yes, while these two are, these two are strongly interacting galaxies. So we found, yes, that about 4 of our objects are in single galaxy, and not in other kind of.
But even in those cases where you saw just a single galaxy, they clearly show evidence of have been disrupted recently because they have a very strong spiral arm.
Yes, yes, yes.
My second question is connected to the metallicity of the regions where the supernova are. Have you got any evidence from other photometry bands?
No, but we study the morphology and the chemical properties of the galaxies using the literature. For example, in I don't remember if this is the case. This supernova is exactly inside each two regions, and this galaxy is very high, contains very high metallicity. But we didn't study in detail the metallicity or the distribution of the metallicity inside the galaxy. We check this aspect only through the literature.
Any other question?
In your sample, I think you have discovered a number of interesting features and trends, so that from them you can keep doing a search, looking for different samples, different targets. In particular, you show that it is true that the higher the star formation rate, the higher the probability to find a supernova. That's clear. But also you have a caveat in this sense that you find that the places where you have the highest star formation rate, you have the lower detection limit.
Yes, exactly.
Right. So, but probably you now are in the situation to be able to use a different parameter, like can be the surface star formation rate, which somehow will allow you to find a reasonable number in which you still have a reasonably high number of possible supernova, and still being able to detect things a bit better. So my question is, would it be possible from all the parameters you have covered, after all in your work, to be able to define another niche for the search in galaxies, which, although they are not so luminous like these merger systems, still have a likelihood to have supernova high enough so as to deserve to search for them? Would you be able to, do you think you will be able in the future to select a subsample with things which are
yes,
still...
Yes, it's a good question. I don't know exactly, but I think that more of these results, at the moment, in my opinion, it's impossible, not impossible, but for example, there are other groups that use adapted optics, that is an advanced way to search supernova, in particular in the nuclear regions. But they found only few obscured events. This is due to the time that we have to spend to search supernova using adaptive optics. And another point is that the field of view is very small, so you lost all the supernova in the outskirts. So it is a good point, but
because I was thinking that on top of your scientific case, which is interesting, is to assure whether the census is biased by a reason that you have explained are reasonable, there is something else, which is the identification of such a thing is a way of dating the starburst somehow.
Yes.
If you assume I mean, in fact, the supernova has a lifetime, and then you are able to say that there is some hint of this to be happening in a particular place. This is like an extra parameter to somehow tie something which is very uncertain, which is the age. That has to do with the model that we use to simulate the right. So this could be an extra, not only by the detection, which is important, but also a way to use it for something more. And for that, it would be important, maybe not only or not to have to assure that you have them all, which is important or not, but just to be able to detect some. That could be interesting to explore.
An important point. But another point is also to obtain a more detailed map of the star formation distribution, because as you can see, it's a crucial parameter. The expected rate can vary so much. So, yes.
Thank you.
Any other question? Okay, so remember you can keep discussing with Matteo in the scientific coffee in the library, and let's thank again him for the talk.